All right, everyone. So for the final part of this unit, we're going to be looking at something called titration curves. And titration curves are pretty simple. It's basically a chart, and it shows how the pH changes in a titration as you add the base to it. Now, you can obviously do it the other way. It could be added acid depending on what you're dropping. But in this situation, we're going to be looking at how the pH changes as you add base. So what that means is you have your container, you have your acid, and you're going to be adding base. Okay, so let's take a look at how the pH will change. Now, if you take a look right here, we are adding base to acid. So before we add any base, so when we're at 0, what we're going to assume is that the pH is going to be less than 7. So let's say this is 7. This is when it's neutral. And if you just have acid, we know that acids have a pH less than 7. So we're going to start just underneath 7. And as you add base, what's going to happen is the acid and the base are going to start reacting with each other. And when acid and base react, they neutralize. And so you're going to end up with less acid. And so what's going to happen is the pH is slowly going to go up. Okay, so here pH is going to increase, okay, as acid plus base neutralizes. Okay, so if we wanted a general equation, you have acid reacting with base, and it's going to produce your conjugate acid, and it's going to produce water. So pH is naturally going to go up. All right, so as you add more base, the pH is going to go up, and then you're going to get to this part, this really steep line, and this is where you get to equivalence point. Okay, and equivalence point is where you have an equal number of acid and base. Okay. Now, basically what happens is as you get closer to equivalence point, the pH starts to spike as you get closer and closer to equivalence point. And once you get past the equivalence point, all the acid has been neutralized, and all you're doing is just adding more base. So in here, it's all neutralized. And if you just keep adding base, you're going to have a pH that is greater than 7 because it's basic now. Okay, so that's the key thing to notice about titration. You first start with only acid. So that's the first part. So right here, this is only acid. And then as you add base, the pH starts to go up. And then you get to a point called equivalence point, where the acid is equal to the base and the acid is completely neutralized. And then afterwards, you have only base left over. Okay, so on your exam, you'll be expected to draw a titration curve, and it should look something like that. And there are a couple things that go into this, but that's the general gist of a titration curve. Okay, now, if you were doing it the other way, so for example, I'll do it in blue. Let's say that instead you are adding acid. So let's flip the scenario, right? Let's say that you had a container of base and you're adding acid to it. Well, if you only start with base, your pH will be greater than 7, right? And then as you add acid, your pH will start to go down until you get to equivalence point. From there, you'll have that spike down, and then it'll go because you only have acid. So if you are doing it the other way, it's just a flipped version of the titration curve, because if you only have acid, the pH will be less than 7. If you only have base, the pH will be greater than 7. So you're just pretty much flipping it because you're starting at different spots. All right, now there are a couple things to talk about titration curves, because depending on whether it is, depending on the Ka of the acid or the base, the acid that you're looking at, is going to change the curve. So if you remember what the Ka tells us, it basically tells us how much of the acid is going to dissociate. So if you have a strong acid, the stronger the acid, that means you're going to have more dissociation. That means more of the acid is going to dissociate, which means that your Ka number will be greater. And that's going to change the way the titration curve looks. So if you take a look right here on your workbook, you'll see a bunch of different titration curves. And you'll see how as Ka goes up, as you get a, as as the Ka value goes down, right, the titration curve looks a little bit different. So here you have a strong acid, and if you look at a strong acid, you'll notice that the curve is very flat until you get to equivalence point, and then it spikes straight up. But as your Ka value gets lower, so basically the weaker the acid gets, you'll notice, first of all, your starting point is higher because the weaker the acid, the higher the starting pH. But you'll also notice that the curve is higher, right? If you look at a strong acid right here, it starts flat, stays flat, and then spikes. But the weaker the acid gets, you'll get a jump. It'll stay high, and then it'll jump again at the equivalence point. So that's something to keep in mind. So if you're comparing two acids together, depending on how strong or weak they are, so the stronger the acid, the flatter the line should be, and the lower the line should stay until equivalence. But for a weak acid, you're going to have a jump. It's going to stay flat and high, and then jump again. So that's something to keep in mind depending on the Ka. All right, we're also going to take a look at some things you can derive from a titration curve. So here we have a titration curve, and I want you to pause the video real quick, and I want you to look at it, and I want you to determine, is this a strong acid or is this a weak acid titration? All right, so we've come back. So if you take a look right here, our acid is going to be HNO2. And it looks very similar to one of our strong acids, HNO3, nitric acid. But this is HNO2, so this is not a strong acid. This is a weak acid. So that's something to keep in mind. If you got that wrong, make sure you just memorize your strong acids, strong bases. Again, it's going to be important for this unit. So this is your weak acid. You are adding OH minus to this. And if you read the problem, I know I didn't ask you to do it, but if you read the problem, it comes from KOH, and this is a strong base. So you are adding a strong base to your weak acid. And then right here, it's going to react. It produces NO2 minus. And this right here is going to be your conjugate base. And then obviously we have our water. All right, so there are some important things that we can get, some important information that we can get from this titration curve. So when you have a titration curve, we can break it down into 4 different sections. Okay, and the 4 different sections are going to be as follows. The first is at when the volume is equal to 0. So I'm going to write it right here. So the first section is when you have only your acid. Okay, and that's going to be when volume added is 0. Okay, so the volume of your base is equal to 0 milliliters. So it's going to be this part right here. So this is going to be section 1. All right, and for section 1, this is where you have only acid. So the pH is going to be less than 7. All right, the next section is going to be halfway to equivalence point. So we're going to take a look at equivalence point. Equivalence point is this big spike where the acid and base start to equal each other. And if you look at equivalence point right here, you'll see that equivalence point is at 20 milliliters. Okay, so I'm going to just jot this down right here. Equivalence point is 20 milliliters. And this right here is when the amount of acid is equal to the amount of base. All right, so the second section is before halfway to equivalence point right here. So I'm going to label this right here. So we're going to write that the second section is before 1/2 equivalence point. All right, and what's special about before you get to halfway equivalence point is that you're going to have more acid. So the acid concentration is going to be higher than your conjugate base concentration. So the conjugate base. So in this situation, you're going to have more HNO2 than you will have NO2 minus because the base is being added, so you are reacting, but you still have more of the acid. But once you get past halfway equivalence point, this will be section 3. So this is going to be after 1/2 equivalence point. Okay, until you get to equivalence point. So this section right here, you're going to actually have more conjugate base than your acid. Because what's happening is your acid and base are reacting, and you're making the conjugate base, but most of the acid has been converted to the conjugate base right here. So you're starting to have a shift in the ratio where you have more conjugate base. Okay, now what's special about this part right here is that the pH at halfway equivalence point is actually very special. It is equal to the pKa value. Okay, so you can use this graph to find pKa and, in that effect, the Ka of this acid, because at halfway equivalence point, that's the pH is going to be equal to the pK. So if we take a look at this as our example, this is our halfway equivalence point at 10 milliliters. The pH, if we look at it, is slightly above 3, right? Just very slightly above 3, not halfway yet. So if there's a question, so if you actually look at 1270, it's asking estimate the pKa value. You should give a pK value from somewhere around like 3.1 to 3.4, and that's going to be the pKa of this solution. Okay, so that's a key thing to know. The pH at halfway equivalence point is equal to the pKa. And then the final section is when you get past equivalence point, that's going to be where you have only your base. And we don't really look at that very much, but that's our last section. Okay, so the big thing here is to note before halfway equivalence point, you have more acid than conjugate base, but after halfway equivalence point, you have more conjugate base than you have your acid. And so that's how we can answer 1270. The pKa of this weak acid solution based on this graph is going to be somewhere between 3.1 to 3.4. Okay, so the pH at halfway equivalence point. All right, so what we're going to do is we're going to take a look at this graph, and we're going to use it in order to solve the last 3 problems for this unit. So the first question, 69, is what is the initial concentration of the HNO2 solution? And so basically, if you read this problem, you're going to see that you have 100 milliliters of your acid. So the first piece of information that we have is that we have 100 milliliters of our acid. And then what we're going to do is we're going to figure out how much base did we add in order to neutralize it. So if you take a look at the graph, you'll see that equivalence point is at 20 milliliters. So equivalence point is going to be at 20 milliliters, which means that we added 20 milliliters of base. We also know that the base is 0.1 molarity, so we can use the molarity formula. Molarity is moles over liters. So that means 0.1 molarity is equal to moles over the volume added, which is 20 milliliters, 0.02 liters. That means that we added 0.002 moles of KOH. All right, now we know that equivalence point is when acid and base are equal. So that means that if you have this value of base at equivalent point, that means we started with 0.02 moles of acid. And so since we're looking for the initial concentration of our acid, all we got to do is divide it by the initial concentration, because molarity is moles over liters. We have 0.002 moles of weak acid. The original volume was 100 milliliters, so 0.1 liters. So that means the initial concentration was 0.02 molarity for our acid. All right, so we can use equivalence point to figure out how much base we added. We know that at equivalence point, the base and the acid are equal, so 0.002 for our acid, and then we just divide it by the original acid volume. All right, for 1270, we talked about how to do this. The pKa, using the graph, we look at halfway to equivalence point. Equivalence point is 20 milliliters. Halfway is 10. And we just look at the pH at 10. And it's going to be somewhere between 3.2 to 3.1 to 3.4. Just needs to be between 3 and 3.5. Because if you look at the graph, you'll see that it's above 3, but it's not quite halfway. So anything between there should be fine. All right, last question of the unit. It says, during titration, after 15 milliliters of base is added, which species do you think will have a higher concentration? The weak acid or the conjugate base? So we're going to take a look at our graph. You'll see 15 milliliters. Now, the key things to look are at equivalence point and halfway equivalence point. We said that before halfway equivalence point, we are going to have more acid than our conjugate base, because the base is still neutralizing the acid. But once you get past halfway equivalence point, you are going to have more conjugate base than you have your weak acid. And if you look at 15 milliliters, it is past halfway equivalence point, so you would say that you'll have more NO2 minus. And the reasoning why you have more NO2 minus is because you are past halfway equivalence point. And you can say something along the lines of more than half of the weak acid has been neutralized. All right, everyone, and congratulations, you have finished the longest unit of AP Chemistry. Just got 2 more short ones to go, and you are all done with the course.